In part 3 of our engineering portfolio project, what we're going to be doing here is we've left the world of linear equations and quadratic equations, and then we saw all about how to solve a system of equations using either matrices or specifically matrices in Cramer's rule. And so in part 3, we're going to the rest of the class. It's all about trigonometry. And again, with trigonometry, it's all about being able to rotate a radius around a circle in a circular pattern. It has a fixed end, and then we just take the opposite end and rotate it about that fixed end, which thus forms the circle. And of course, as you start to rotate anything like a fixed arm, it's going around in a circle, it's creating an angle, you're rotating it through an angle, and where it lands at is a coordinate value along that circle. Okay? Well, obviously in the world of engineering, we don't always have like the typical unit circle where the radius is 1. What this is really focusing on is what to do when your arm length is not 1. Okay? And that's exactly what this picture is all showing you basically, is that you could have, let's say, a robot's arm, and you're telling this robot, okay, I want to start here. You're programming it basically. If you want to program a robot just to like move a finger or something, consider this arm maybe its finger. Okay, and what you're doing there is you're telling the robot, okay, we're going to start at this position, we're going to rotate it either 30 degrees, or you can say I'm going to rotate it to this specific point, and then you say run or say go, and it's going to run that program and go, okay, move my finger from flat to up, and it's going to land at that specific point. Okay, and typical, just the same thing as if you rotate going counterclockwise with that, you're doing a positive angle, and if you go clockwise with it, you're going to do a negative angle. Okay, so all this should look a little bit familiar. The only difference is instead of our radius being a 1, we have a radius being something other than 1. So this specifically, these next points right here, is really connecting the two between each other. Okay, we've always had that typical unit circle where x squared plus y squared equaled 1 squared. But the only difference here is instead of 1, we're taking that way, and our radius is going to be L. Okay? And if I ever asked you to solve for the length of an arm, we're going to use this formula right here, which is Pythagorean's theorem. Just solve for L, solve for the hypotenuse. Okay? And then anytime we want to find cosine, remember in the whole like SOHCAHTOA, cosine is our x value, always relates to our x value, but it's always our x values over the hypotenuse. Well, in this case, our hypotenuse is L, and our y values, our sine values, are our y values divided by the hypotenuse. So if we just rearrange this first formula, you'll get x to be L cosine theta and y to be L sine theta. Okay? So instead of x just being cosine theta, the difference is when our arm length is not 1, then we just have to multiply it by L. And when our arm length is not 1, again, we multiply our y value by L. Okay? So those are the key concepts. If you're solving for L, just use basically the Pythagorean's theorem. And if you're solving for the coordinate values x and y, meaning what I'm rotating L to, I'm going to rotate it through this angle. Where am I going to land at? What coordinate? And this is how you're going to get your x and y coordinates. Okay? So let's go down to example 1. Example 1 is saying that we have an arm length, we're just going to still call it L, and we want to know that if I rotate this 120 degrees, where am I landing at? Okay, so the values are, the x value is just your L times your cosine theta, so x is going to be L times the cosine of 120 degrees. Y is L sine theta, so y is L times sine of 120 degrees. So when I plug these into my calculator, I'm going to get the cosine value of 120 degrees. It'll be L times, in the 120 degrees, I guess you really don't even have to have a calculator because this is specifically on our unit circle, and thus should be kind of a value that we know. So the x value of 120 degrees is negative 1/2. So we can say basically x is equal to negative L over 2. And then here, the sine value, the y value, is the square root of 3 over 2 at 120 degrees. So you can say then y is L times the square root of 3 over 2. and that's where they will land at. So basically then as soon as I know what L is, then all I have to do is plug that in and I can actually get my definite coordinate. Another way to look at this problem is, you see how I drew kind of this 60 degrees down here? It's realizing, 120, if I'm going to go the rest of the way over to the 180 degree axis, it would be 60 degrees left over. So what we could really look at is the same thing of saying, if x is equal to L times the cosine of 120, if I wanted to use the remaining 60 degree angle, I could also say it equals the negative L times the cosine of 60 degrees. And negative L because you're in quadrant 2. This is a way of using a reference angle. Okay? And y is equal to L sine of 120. Well, the reference to that would then be L sine of 60. And this one's positive because your y value is up in quadrant 2. The remaining bit is going to be positive. And that would get you the exact same way. Of course, it's going to be then negative L over 2 there, and L square roots of 3 over 2 right there. Okay, let's move on to the next example. Okay, same one again, or pretty much a similar one, in the sense of you want to find x and y for 225 degrees. If I use the basic formula, then we can find that x is going to be L times the cosine of 225 degrees. Y is going to be L times the sine of 225 degrees. Okay, again, 225 degrees we definitely know. So for x value, it's in quadrant 3, so it's going to be negative. It'll be negative square root of 2 over 2. So x is negative L square roots of 2 over 2. And the y value is also going to be the exact same thing, because in quadrant 3, the y values are also negative. Okay, and if I want to try this problem again, kind of using the reference angle rule, what the reference angle to, I'll write it out like this, reference angle of 225 degrees. Remember, in quadrant 3, the rule says 225 minus 180, so it's 45 degrees. So in that case, then we can say x would equal L times the cosine of 225, which is equal to the negative L cosine of 45 degrees. And then y is equal to L times the sine of 225 degrees, or using the reference angle, it would be negative L times the sine of 45 degrees. And in both cases, it's going to be the negative L square root of 2 over 2 for both x and y. All right, moving right along, let's go to example 3. Okay. And before we do that, I'm just kind of making a stopping point real quick. Again, we're about to use these formulas where if you want to find L, the arc or the length of the arm, the robot's arm, or whatever this image that you have, it's going to be just the quadratic formula, or not the quadratic formula, but the Pythagorean formula, where it's just the x squared plus y squared and take the square root of it. Okay, and then if I know x and y, then how I get theta is just remember what y equals is L sine theta. Okay, that top part is what was given to us, we just used. X is equal to L cosine theta. Okay, well, in this fraction, L's cancel out, and sine over cosine is just tangent theta. So that's why I'm saying y over x is equal to tangent theta. And remember, anytime you're trying to find an angle and you want to get rid of basically the trig portion of it, you move it over to the other side and use your inverse button. Okay, so always use the inverse whenever you're finding an angle. And that's the other formula we're going to use. All right, so going down to example 3, we want to find L and theta for the points -1, 0 and 0, 1. Well, first of all, let's find the length of that arm. So L is going to be the square root of x squared plus y squared. So L is equal to the square root. And if I choose, first of all, let's go with that first point, -1, 0. Okay, so here's all the steps for that. So the x value squared plus the y value squared. So L is going to be basically the square root of 1, and L is equal to 1. So the length of that arm, of that robot's arm, would be 1. Now to get theta, theta is the inverse tangent of the y value divided by the x value. So theta is the inverse tangent of y, so 0 over -1. And any time you divide 0 by anything, it's just 0. So it's where on that unit circle is tangent equal to 0? Well, tangent sine over cosine. And so when are basically that's saying is when are our y values equal to 0? So theta could technically be either 0 degrees or 180 degrees. But really it's only one of them, because let's go back over here and graph. Let's look at this. If I wanted you to graph the point -1, 0, it's right back here. So it's like saying that robot's arm is just sitting right there. Well, does that look like at 0 degrees, or does that look like it's at 180 degrees? Well, it's 180. So specifically, since we're at the point -1, 0, then our theta is just 180 degrees. So the length of the arm at -1, 0 specifically is 1, and then the angle itself is 180 degrees. So now if we go to 0, 1, the point, then L is going to be the square root of the x value squared plus the y value squared. So L is again the square root of 1, which is 1. All right. And then theta is equal to the tangent inverse of the y value divided by the x value. Well, y value divided by x value, it looks like basically we're saying tan inverse of anytime we're dividing by 0 is undefined. Well, and we're used to, when we see this undefined thing, just stopping the problem and going, I can't go any further. But no, let's come back to this real quick. Because basically what this is saying is this is going to occur where tangent's undefined is when your x values are 0. Okay? Well, our x values are 0 along the y-axis, which is going to be either at 90 degrees or 270 degrees. So you can say theta is equal to 90 or 270. And then again, just like the problem before us, we're looking specifically, if I graph the point 0, 1, that means your robot's arm is just kind of hanging out right up here, which is definitely 90 degrees. So we're going to focus more on that. If our coordinate was instead to graph or to find all the information for 0, -1, then the arm length would still be 1. It's just that theta would be then, in that case, 270. Okay? Well, let's keep going on.